Okay, good evening everybody. I hope everyone's having a wonderful day. So today we're going to be talking more about Big O, and depending on how far along we get, we might start talking about recursion, which in itself is a very interesting topic. So today I'm going to be spending some time working through some more examples using Big O. We'll see a few different ways we could use the definition of Big O, and maybe some properties involving Big O. So I thought we'd start off by just kind of rehashing where we were last time. Where last time I pulled out the definition of Big O and we were using that to establish Big O claims, showing one complexity function is Big O of another complexity function. So I thought we would do another example before I kind of start trying to give you some interesting little pointers, like just generally about how you could approach these. So let's try proving this claim using the definition of Big O. So the first thing I want to point out is that usually I'll just tell you what I'm trying to prove. Usually it's a good idea to lay out your game plan. And the main reason why I'm going to do it this way is so that I can invoke the definition of Big O in my conclusion. So if I find the pieces that I need to prove the Big O claim, it's quite simple. I find those constants, then all I have to do is pull out the definition and say, hey look, here's the C and N0 that I need that meets the definition for Big O. So we need to find constants. So remember, we have to find these two constants. We need to find constant C. So now C is a positive real number, and N0, which is a positive integer. Remember, positive integers, they start at 1, go 1, 2, 3, 4, 5, 6, all the way up. Such that for all n greater or equal to n0, 3n squared plus n is less than or equal to c times n squared, right? This is, say my definition, I had f and g. This is f, this is g. So I'm just substituting those in to the definition. So what I'm going to do is I'm going to try picking up the technique I showed you last time, where I was using a bucketing strategy, where what I did was I tried to group things on the right-hand side so they looked a lot like what's on the left-hand side. So I'm going to pull out this little technique. It makes things a little bit easier to play around with when we deal with functions that look like polynomials, just like this one, which this is a polynomial, it's just a quadratic, right? So if we have polynomials that have a form like this technique tends to work quite well. So based on what we did last time, if I have 3n squared plus n, does anybody have any suggestions of a c? Think of, based on, yeah, I see it in the chat. Excellent, excellent. I'm seeing some fours. Four is a really great suggestion. So what I'm going to do is I'm going to pick c is equal to 4. Then I got to tell you what the rest I have to do. I have to find that n0, right? Then we find n0. We find n0 such that for all n... Oh no, the turtle friend left! It left us! No! The turtle went to go have a little nap. Turtle's okay though. We're all good. So I'll come get you later. Such that for all n greater or equal to n0, we write 3n squared plus n is less than or equal to 4n squared, right? Now, here's what I'm going to do is I'm just going to make it. I'm going to expand out this. I'm going to distribute it into terms that look kind of like what's on the left-hand side, so that I can compare each one of these terms against whatever I have on this side. So if I make this into two terms, one is 3n squared, then I have another one that's n squared, I can compare the 3n squared against 3n squared, and I compare the n against the n squared. Now, I must stress that this strategy is quite easy to use with polynomials, but always remember, if there's an explanation that's much simpler to use it. For example, if you know that this inequality is in fact equal for all n values, like for all n, don't use the strategy that you don't necessarily need to use, right? So if you know, for example, oh yeah, no, this inequality works, and it's straight up obvious where they're like two numbers that they're the exact same quantities on both sides, where there's no real justification beyond, say, oh, notice I have to say a little bit more here. It's not as straightforward. But most certainly if I had two numbers that were the exact same on both sides of the inequality, like if this was, say, 4n squared, like it's not 4n squared here, but if it was 4n squared is less or equal to 4n squared, you most certainly don't need to pull out what I'm going to do next, right? You could just simply say, hey, the left-hand side equals the right-hand side for all n greater or equal to 1, right? We're going to just pull out the trick that I did last time. But like I said, you don't need to go that far if it's a little bit simpler. Just always think about the way you justify what I'm trying to say. Because remember, I'm trying to just find that n0 at this stage, and I'm trying to justify it for you at the same time. Almost like I'm revealing to you a chocolate bar out of my pocket that hasn't melted. Now, if I had a chocolate bar in my pocket, which I should have had, I would present it to you. And that's what I'm trying to do when I present these arguments to you. Notice that I'm going one step to the next, to the next. I'm not just pulling the chocolate bar out and throwing it at you. That's not fun, right? Especially if it was melted. Please don't do that. It's not pleasant. I speak as if this has happened to me. I'd rather not say. So anyways, what we're going to do next is I'm going to try to do what I said previously. Notice that. So I'm going to try to rewrite this inequality so it's a little easier to play around with. Notice that 3n squared plus n is less than or equal to 3n squared plus n squared, which of course this is 4n squared, right? But we know that. So remember, this is the reason why this inequality is true. It's actually this part I'm offloading on the backside of the sentence. As 3n squared is less than or equal to 3n squared for all n greater or equal to 1, and n is less than or equal to n squared for all n greater or equal to 1. Now, if you ever find yourself looking at those and you're saying, okay, how do I justify these claims? Well, in this case, you just divide both sides of the inequality by whatever on both sides. You get 1 is less or equal to 1. In the second case, if you divide both sides by n, you'll end up getting n is greater or equal to 1. If you need to really kind of break it down a little further. So, question, what should I pick for n0 here? A very natural choice. I like that one. So I'm going to pick n0 to be 1. Now I must stress, if I told you I picked n0 to be 2, that's also correct. If I picked n0 as 3, that's also correct. I'm just going to pick a very natural one for my argument. So notice that all of these statements that I have here, actually, let me add one. Let me see if I got it in here. Notice that this is less than or equal to that is equal to this. For all n greater or equal to 1, I can say this right here. For all n is greater or equal to 1, because this statement is true for n is greater or equal to 1, and this one is true for n is greater or equal to 1. Yeah, you can do it in several different ways. If you want to use a different algebraic approach, you can certainly factor things a little differently. Most certainly. Can we pick n0 to be 0? No. Because remember, n0 is defined to be a positive integer. That's a wonderful question, by the way. Make sure, remember, n0 is a positive integer, meaning it has to be 1, 2, 3. It starts at 1 and goes up. So, we're going to choose, and 0 is equal to 1. Therefore, by the definition of big O, 3n squared plus n is big O of n squared. And we're done. But yes, so just remember the big game plan. Find C, find n0. Typically you'll find that picking one of the constants makes it easier to argue for the other constant. You'll find almost in all my examples, I will usually pick C first, then n0, but you don't have to do it that way. You could easily pick n0 first, then derive a C that works. There's not one universal rule for doing this, but the point is at some point you have to present me C and you have to give me n0. And they have to be justified. So notice that whenever I did this, right? Did you notice that every time I wrote down a sentence like these inequalities, notice that I didn't just blindly write them down, right? They always had something that tells me, okay, so I noticed that this statement is true for all n is greater or equal to 1 as, and here's a reason why. As opposed to me just writing this inequality down with no statement of what n is, or am I trying to show it's true, or am I trying to show it false? This is stuff that's important to contextualize your argument. Make sure you don't just blindly write down inequalities without anything kind of attached to it. So for example, if you don't tell me like what you're doing with your proof, it's very hard to know what's happening. Now, how do you test C and n0 in one equation as a solution? Now, you have to be a bit careful. So notice that the way I approach this, I used very basic counting techniques to derive my C and n0. So notice that I don't have, to test them, I just look at the arguments, right? So notice that my arguments here justify the selections of C and n0. So these statements are true for when I picked C to be 4 and n0 to be 1. If you plug those into this first sentence that I have, which you could get from the definition, if you plug those in, you'll see that this inequality should hold when I put C is 4 right here, and I put 1 right here. Now, I must stress, one thing you have to be careful about is if you take on one of the approaches I mentioned last day, root solving. If you tend to use that approach, you might find yourself running into a couple of troubles when you start dealing with tougher looking polynomials. But the other reason you have to be careful is that you have to make and determine the behavior of the functions. Because sometimes because when you're doing and trying to solve for certain things, such as n, you may find that, okay, well, when I get an n value, if I was trying to solve, note that you'd be solving over an inequality. So there's some presumption about the behavior of the function for the left side and the right side. So just be careful if you take on that approach. You might have to say something about what the functions look like. Are they increasing functions? Are they... So do you see how this makes it a little bit easier to play around with? And keep in mind, this isn't the only way you can argue things, just to be very clear. So is it okay to conclude using the set theoretic way? Yeah, that's perfectly fine. So notice that when I use the word is, you could have written that set theoretic in, that's perfectly fine. Wherever I use the word is like this, you could put this symbol there if you like. If you want to, you can also use this equal sign, but remember, this is not an equal sign, right? It's just a convention. Any of these are perfectly fine to use. So yeah, so somebody was asking about if they could, instead of writing is here, they could write the set theoretic in that I talked about the other day, or this symbol. Either one's fine. Any of these three is perfectly fine. Okay? So was everybody okay with this example? I wanted to highlight a technique. Let me just give our little turtle friend a kiss. There we go. See, I'll put our turtle friend right here. There we go. So, see, I told you I was going to come back. So I want to show you an interesting thing about what we just did here. And in our previous example, but like I said, remember, you can pick different C's and add zeros. Now, there's another example I put in the notes that involves fractional coefficients. So like, I think it's Let me just actually jot it down here. There's another example in the notes. It's 1/4 n squared plus 2n plus 2 is big O of n squared. I'll let you take a look at this in the notes. But you can actually adapt to pretty much the same idea I did over here into this one example. Now, you might ask, why? Actually, before we proceed, without arguing and presenting the argument like I did over here, does anybody have any suggestions of how maybe I could approach the C and N0 in this case? Any suggestions at all? So keep in mind there's many of them that work, but there's if you think about the pattern, you may be noticing a pattern over there that looks awfully suspicious looking. Yeah, I see it in the chat. So if you were to, for example, pick 17/4 for C, you could make N0 be 1 in this example. But remember, just stating these two constants is not a proof. You still have to justify why they work. Yes. I see that some have caught on to this. I'm wonderful. So I want to give you a general rule for dealing with polynomials. So I'm going to state the property, and then there's also another example that's within the confines of the presentation of this property. So I'll encourage you to take a look at that in the notes. Like I said, I gave several examples. So there's a very simple way. There's a simple but effective way. A simple but effective way of handling, means somebody gives you it and asks you something about big O with it. Handling polynomials of the form. So it'll look something like this. Suppose I give you a polynomial P, and I have A0 n to the k plus A1 n to the k minus 1 plus all the way down to a k minus 1 times n plus ak. Where, now you might ask what all of these things I just wrote on the board are. All of the a terms, these are what we would refer to as the coefficients of the polynomial. I do have a question. What's the highest order term in this polynomial? What is the largest exponent here, just to be clear? So remember, I didn't really say, I told you it's k here. So keep in mind, you can make, this is a very general form to play around with. If you want to make k is equal to 2, you can make k is equal to 2. If you want to make k is equal to 3, you can make k is equal to 3. In fact, you can take any one of the examples I've shown you so far and make it look like this by plugging in certain values for k and changing up these a values. So now I've got to tell you about these coefficients, where I think it's A0. I think I wrote down A1 in my notes. So I got A0, A1, A2, all the way up to AK minus 1. All of these are going to be real numbers. So I'm going to just assume that this polynomial is a complexity function. I'm going to assume that it takes on positive values, but keep in mind, by the selection of these coefficients, sometimes you can actually pick them so that this function is negative. I'm not going to presume that we're going to play around with those kind of functions, but there are very easy ways to get around that, but we haven't defined our big O notation to really handle that. We're just keeping it strictly to complexity functions that we would encounter when we analyze algorithms. So just to be clear, so this is P right here. And now here's the statement. Give an integer constant k greater or equal to 0 and coefficients above. P is big O of n to the k. Which ones are the exponents and which ones are the subscripts? Okay, so the last two terms, it's a with a subscript of k minus 1 times n to the power of 1. And the final term is a sub k. Whoops, I think I'm missing a k here. Let's get that k in there. Let's get our ak in there. And this would be n to the power of 0, but n to the power of 0 is just 1. So all the powers are just descending from the highest one. So you might ask, Dan, how does this work? Believe it or not, I'm hoping that you may have caught on to what I've been up to lately. So if you want to get the sketch of how you would play around with these, here's the sketch. I have the full proof in the notes. I'm not going to test you on it. I just want you to get the general idea here. So what you would do is you pick C to be, you take the absolute value of all the coefficients. So a sub 0 with the absolute value plus a sub 1 with the absolute value, a sub 2 with the absolute value, all the way up to the absolute value of ak. And here's the neat part. Here's the neat part. And you make n0 is equal to 1. So, for example, you might ask, where did 17 over 4 come from? Well, you look at the quarter here, plus a 2 plus a 2. Notice that if you add those up, you get 17 over 4, if you play around with the fractions a little bit. And note that the absolute values there, that just drops out the sign. So if you ever had to have a coefficient that's a negative one, you could just simply, it gets rid of the negative signs. But yeah, no, so you'll find that when you run into polynomials, this approach will always work. It's rather helpful. Are there any questions about this? This is a rather nice strategy that we could use very often when we're dealing and trying to prove big O claims. But yeah, whenever you encounter polynomials, most of the time this strategy will work for what we needed to do. So if it has this form and it has this kind of structure to it, it's a complexity function, then yes, this whole idea will work, and it's based on selecting those two constants. But if you want more details, just take a look in the proof in the notes. Okay? So I've included another example that follows right after this, showing you how you can plug in the coefficients if my example up here wasn't really clear about that. But anyways, that brings me to talking about a different set of claims. So remember, when you're trying to prove big O claims, we've seen some ideas. We've seen how, okay, we can make it look kind of like what's on the one side of the inequality. If sometimes we have to pull out some understanding of how the functions operate. These are all things you have to take into consideration when you're doing this. I want to switch gears now. And I want to talk about if I wanted to prove something is not big O of a something. Before I proceed, are there any other questions about proving big O claims? About proving is claims? Saying one complexity function is big O of another one? But remember, if it all fails, go to the definition. Just plug in your functions and see what it's trying to tell you. So is it crystal clear how we did that? So remember, we find the C and we find the N0. If we're okay with that, give me 2 thumbs up before we proceed. Okay, wonderful. So let's start talking about the other direction of this. Showing F is not big O of G. So a quick question. Do we get N0 and C, then prove that we have to do what with them? Okay, so just remember, when we prove an is claim, like F is big O of G, your goal is to identify those two constants in the definition, C and N0, so you get to pick them. So, but your job is to justify their selection as true for the definition. So that actually brings me to a perfect point to talk about this right here. So the natural question is, how do we use the definition of big O to say f is not big O of g? So I'm going to show you a couple of different ways we could achieve this. The first one is going to be quite direct. We're just going to take the definition and we're going to logically flip all of the conditions of big O. So we're going to negate its definition. And at first this sounds like it'd be some daunting task, but believe it or not, the game changes. So my game plan that I had, remember the game plan was I find C and I find N0 such that the inequality holds that I had for all n greater or equal to N0, correct? The game is going to change because, remember, in that definition, I had to find C and I found N0. Now, if somebody came along to you and said, hey, Dan, how do I show somebody that something is not big O of a something? Well, what did we do when we tried to establish the big O claim? We found a C, we found an N0, right? So does anybody have any ideas of how I would show that if I gave you two complexity functions, how would I establish f is not big O of g if that's the case? Any ideas? Any ideas at all? I'm very happy to see what people are thinking. Ah, yeah, I see a very interesting suggestion in the chat. So you prove that C and N0, now I'll just rephrase it a little bit. Yeah, show that they don't exist. Show that you cannot pick C and N0. See that they don't exist. So no matter what C and N0 can take on in their value, they can't simply satisfy that inequality that I had before. And that's actually all we're going to need to accomplish. So you might ask, how are we going to do that? So let me just first write out what the negation of the big O definition is. And as soon as you understand that, the game plan is that we're going to show that there's no way you could pick C and N0. But I need to show you a little bit more about the definition and how it changes in relationship with that. And it makes it a little easier to see what we're going to do with this. So I'm going to say we negate the definition. So we could say that f is not big O of g if and only if. So just as a reminder, remember, everything, if I tell you that f is not big O of g, everything that follows after this part right here has to be true. And if this is false, meaning that f is big O of g, then it means that whatever's here has to be false as well. So if and only if for all C and N0, remember these are the same C's and N0s we had before, but it's for all possible ones. There exists n greater than or equal to N0 so that f of n is greater than C times G of n. So you might say, Dan, so walk me through this, Dan. I'm having a little bit of a hard time parsing this. So just remember, we want to show that there's no way you can pick C and N0. So what I'm going to do is for all the C's and N0s that could possibly be the case, my goal is to identify a value of n as long as there exists an n, as long as it's at least n0, so remember, I don't know what n0 is, right? It could be something I pull out of a bucket, right? And I present them to you. Here's C and n0. I don't know what n0 might be. But it has to be for this n, it has to be so that f of n is strictly bigger than c times g of n. Notice that this is just I just flipped the inequality on you, right? So now all I'm saying is, regardless of what c and n0 are, there's going to always be this n value so that the inequality will be violated from the original definition. So the game plan will be that somebody gives you a c and n0. I don't know what they are. I'll have a fancy way of writing that down for you. Then, well, it's actually really simple, but I like to kind of pump these things up. So that I have to pick this. So notice that in the original definition of big O, I found C and N0, right? Those I had to pick. Now, what you're going to have to pick this time is N. So notice that it says there exists N greater or equal to N0. So now, the burden on us is regardless of what C and N0 are, we have to find this N. And that's actually how we use the negation of big O. We just have to find N. So this is the one approach, the first approach you can take. So there's a couple of ways you could use this idea. So you could prove it directly. That's the first thing you could try doing. So here's one way you could approach this, is you just use what I just wrote here literally. So I'm going to give an example with you. So here's an example. Let's show that n squared over 2 is not big O of n. That statement seems to make sense, right? Because this is a quadratic here, and that's a linear term, right? So your intuition would tell you that this is probably the case, right? But intuition can sometimes kind of mess us up, so let's make sure that we are indeed correct about it, okay? So let's try proving this. Remember, all I'm going to do is pull out this definition and just present it to you. Remember, I usually give you the game plan, right? I lay out the game plan for you, and then I fiddle around with it once I have laid out what I'm going to tell you I'm going to accomplish. So I'm going to let C and N0, and remember N0 is a positive integer, right? So I'm just to make it a little easier for you to remember the fact that N0 is a positive integer, I'm just gonna make sure that I explicitly write this, but you don't have to. Let C and N0 be arbitrarily chosen and fixed. Now you might ask, Dan, what does that mean? So remember I told you that what I'm going to have to argue has to work regardless of what C and N0 are. So imagine I had a big bucket and had a bunch of fish that are friendly and swimming around in the bucket. And I come along and I say, okay, well, I'm going to dip my hand into this fish pond and I'm going to hold one of my lovely fish and I'm going to hug the fish. So if I pull out this fish and say it has a sticky note on the fish, I don't know why. Let's be nice to our fishies. And it tells me a C and an N0 on the sticky note. I take that off gently. I put the fish back in. It tells me some C and N0. My job is to give you an argument regardless of which fish I pull out of the pond with a C and an N0 so that I could find this N. It's going to sound a little weird at first because we're so used to that big O definition. So I'm going to assume that the C and N0, I just pull it out of the pond. And I have C and N0. I don't know what they are, but my argument has to work regardless of what I pull out of the puddle, or the bucket, or the melted chocolate bar, whatever it might be. So when I say arbitrarily chosen, that's what I mean. I take it out of the bucket, and I say fixed, I mean I'm presenting it to you. So now this is where I lay out what I'm going to do. We need to find n greater than or equal to n0 such that n squared over 2 is strictly bigger than c times n. So I've laid out the game plan, okay? So now notice that I've told you what I'm going to accomplish here. My goal is to find n. So all I'm going to do now is I'm going to make some simplifications to my inequality over there and see if I can make it so it spills out some relationship between c and n so that I can try to make sure I can pick an n that's big enough. So here's the idea. Here's one way you could do this. So notice that n squared over 2 is greater than c times n, if and only if. It's okay if I abbreviate if and only if with IFF. So all I'm saying is you could rewrite that inequality in the following way. N over 2 is greater than c. Does everybody see how I did this step here? Now, if ever it's unclear to you what you're doing, so notice I'm just assuming that you know what I just did over here. So notice that I say n squared over 2 is greater than c times n. Well, if I divide both sides by n, I end up with n over 2 is greater than c, right? That's all that happened here. So notice I'm just rewriting what the inequality says. So note, I'm not saying anything about whether the statement is true or not. I'm just rewriting the inequality. So for example, you could have easily said, simplifying the inequality, we get blank. So now I'm just going to rearrange this, implying n is greater than 2 times c. So I'm going to multiply 2 to both sides of this inequality. Now I have n is greater than 2 times c. So I've just multiplied both sides by 2. So now we have something interesting we could play around with. So look, I have n is greater than 2 times c. Now, I don't know if this statement is true or false. I'm going to try to find a value of n that's going to work. So remember, I just have to find one value of n that's going to work, regardless of what c and n0 are. So you're going to notice there's something I have to be very careful about. Notice that I don't know what c's value is. I also don't know what n0 is either. So I'm going to have to take this into account when I pick my value for n. So watch this. So pick n to be the maximum, the max of n0. And now I'm going to use a little bit of a different notation. I'm not sure if you've seen this before. But let me explain this. So you may or may not have seen a max function before. Has anybody never seen a max function before? So just to explain this, a max function, you take the largest of the values that are among the arguments. You may have seen it, say, for example, in a programming language. So for example here, if n0 is bigger than whatever this is, I take n0. If this the second term is larger than n0, then I take the second term. So note, I can have as many parameters as I like for the max function. So it just takes the biggest of the values. That's it. That's what the max function is. The other one is I want to address what I just wrote here with these upper angle brackets. They're not angle brackets. These upside down L's. Has anybody never seen those before? I'm happy to explain it because usually I have to anyways. So you may have seen two concepts before. You may have seen something called the ceiling function and the floor function. So there's two functions called the ceiling, and then there's one called the floor function. So the ceiling, so what you do here is you round up always to next integer. With the floor, you always round down and you drop the fractional part. So just as an example, if I give you the ceiling, of 4.2, the ceiling of 4.2 would be 5. So if it's bigger than 4, but it's not quite 5, it automatically will round it up to 5. So the ceiling is denoted with these brackets like this. The floor is indicated with brackets that look like that. So this is an example of the ceiling function. The floor function, if I did the floor of 4.2, I should end up with just 4. So you actually are quite familiar with the floor function. We use it all the time when we do integer arithmetic in programming languages, very often. So for example, if you divide one number by an integer, do you hang on to the fractional part? No, right? So that's this. There's a question about rather than do c is equal to 1/2 condition. So keep in mind, we're not going to be picking c and n0. We need to show that we have to pick n in this case, just to be very clear. So remember, my goal is to pick n here. So that's what I've selected here. You might ask, Dan, why is this selection the one you want to go for? So I want to make sure n is big enough. So notice that n has to be at least n0, but it also has to be bigger. This n value here has to be big enough that it makes this inequality true. Truly, if I round up the value of 2 times c plus 1, this will most certainly be larger than 2 times c. The other thing you have to also keep in mind, and you might ask, Dan, why did you include this ceiling function? It's because remember, the way we defined our complexity functions, were they defined where the input's a real number or an integer? The answer is it's an integer. So when I pick n, it better be an integer. In fact, it has to be a positive integer. So that's why we round this value up. You could have just rounded up the c value if you wanted to. I'm just making sure that I get an integer when I get the result out of this max function. So that's how I picked n. Then let's finish writing up the proof over there, because it's getting a little bit cluttered over here. So I've picked n. So I picked n. What are we going to do with this? Well, now from the algebra I did over there, you should see quite clearly why I picked that n based on what I just said a moment ago. But just in case, I'm going to say, because usually it's a proof, so you got to be careful the way you phrase this. Then we have n greater or equal to n0, which is true because of the max function. This will guarantee that if n0 are larger than this, the ceiling of 2 times c plus 1, then you most certainly will make sure that n is big enough for such that this is true, such that n is at least n0. And for this value of n, the inequality is satisfied. Therefore, n squared over 2 is not big O of n. Big O of n. And that's the end. So remember, the big idea here with a direct proof, using the negation of big O, is you find that n directly, and then your job is just to make sure it works. So in my case, I simplified down the expressions until n became very obvious in its relationship with c. And then I picked the max function to make sure I made sure n0 was big enough. You're going to find almost all the time you're going to run into a case where you're going to end up using one of these max functions to make sure that my selection of n is big enough. So are there any questions about what I just did here? Any at all? I'm going to show you a different approach. I know some students actually like this other approach, so I'd like to show you two different ways of approaching this. Yeah, so usually when you're doing if you're being very strategic about it, the game plan is usually to isolate n out in your algebra. Yeah, no, very good question. Usually that's what happens. But yeah, so believe it or not, there's another way you can prove the claim that f is not big O of g, and it's actually one that is a fairly standard proof technique I'm going to talk about. You can use what is called a proof by contradiction. I know some people prefer using this technique because it only requires you to remember the definition of big O. So it's called proof by contradiction. It's a standard proof technique. So here's the idea in a proof by contradiction, at least in the context of what we're trying to prove. Now we're going to assume f is big O of g, and we're going to try to show it leads to what is called leads to a contradictory statement, which I'll explain what that means in a moment. So just to reiterate, proof by contradiction. So in our game plan here, we'll assume that f is big O of g, and then we're going to try to show that it leads to a contradictory statement. A contradictory statement is a statement that never is true. So it usually means that I make some assumptions, and then I show you that by making my assumptions, I lead to a statement that effectively proves something that makes absolutely no sense, based on the definition we assumed was true. So some students really like it because it's quite natural to use. You'll find that this proof by contradiction technique is something that pops up all over the place. We use it in algorithm design sometimes, maybe not necessarily in this course, but in, say, something like CS 340, it's most certainly something that pops up every once in a blue moon. So I wanted to show you a little bit about it. So here's the idea. So I'm going to show you with an example. And like I said, if you're working on the assignment, you could use either of these approaches. I don't care which one you prefer. If you prefer to use the direct approach or this one, either one's perfectly fine. So here's an example. Let's show n cubed is not big O of n squared. Let's try doing that. So now you might ask, Dan, why are you assuming that f is big O of g? Aren't you trying to show that f is not big O of g? And this is the thing that's interesting. So I'm going to assume the negation of what I'm trying to actually prove, so that if I walk through the definition of big O, that I can kind of cook up a statement that absolutely cannot be true. But it's to the point where I always produce a statement that's going to be false. So you're going to see how this is going to play out when I do this example. So here's the idea. So I'm going to just walk through what I mentioned here. So this is the game plan. I'm going to assume. So some people would say suppose. I'm going to just say assume just to keep this simple. Assume that n cubed is big O of n squared. And one thing I must stress is that we're doing this intentionally to break the statement and show that it can't be true. We're leading to this contradictory statement, the statement that can never be true. You're going to end up with a bunch of gobbledygook that it makes no sense. So we're going to assume that n cubed is big O of n squared for the sake of a contradiction. Then there are constants, right? Because it is, if I'm assuming that n cubed is big O of n squared, then there has to exist those two constants, right? C and n0. They have to exist. Then there are constants, C and n0. And n0 such that n cubed is less than or equal to c times n squared for all n greater or equal to n0. So remember, all this is just me using the definition of big O, right? So now watch this. So watch what I'm going to do here. I'm going to work with this as, remember I made this assumption, I'm going to see what I could do with this to come up with a very silly statement. Since n is greater than or equal to n0, n is positive, so we can divide both sides of the inequality. The inequality by n to get n is less than or equal to c for all n greater or equal to n0. So all I've done is I've just divided both sides by, is it by n or n squared? I think it's by n squared, right? N cubed, n squared, yeah, we're dropping off n squared. So we're dividing both sides by n squared, right? Thank you. These are the kinds of things I like to see people point out. Sometimes I do it by design. So notice that I've just simplified the inequality. We know that this inequality is true for all n is greater or equal to n0 under my assumption. So now I have a statement saying n is less than or equal to c. Does anybody see anything strange about that? There's something odd about that statement, right? What is odd about it? Seems kind of strange for me to say that, right? Is there anybody that has any ideas why, like, is there anything peculiar about what I just wrote there? So remember, it's saying after we divide both sides by n squared, we get n is less than or equal to c for all n is greater or equal to n0. So it's even worse than that. Yeah, in fact, that's actually perfect. So notice that, no, I take that back. You are absolutely right. So notice here that n is less than or equal to c. I'm assuming this is true, right? But there's no way that could be true, right? There's no way that could be true because remember, it's saying that n, for all n greater or equal to n0, it has to be that n is less than or equal to c. I can always probably find a big enough c to pop a bubble in that inequality, right? Exactly. I can try to find an n that's going to absolutely break this whole thing. Yes, and the main reason why is because, remember, n grows without bound, right? There's nothing stopping n from surpassing any one constant, right? So all I'm going to do is I'm going to come over here and say, imagine I have this assumption as my beautiful little balloon over here. I'm going to come along and I'm going to pick out an n. I'm going to sharpen up that n and I'm going to pop it like a needle to the balloon. So I'm going to refute that inequality most certainly can be true at the same time as I pick some other n that's going to be also in that same range. So watch this. So let's do it over here. Let's do it over here. I'm sort of just jogging back and forth here. So, what are we going to do? Well, now, you're going to see that I'm going to adopt a very similar strategy that I did last time. So regardless, R is looking a little too excited there. Regardless of the value of C, N cannot be less than or equal to C for all n greater or equal to n0. Because n is not a constant, and grows without bound. It grows without bound. Hence, so now here's me coming with my little needle, gonna pop the balloon, okay? Hence, for example, if n is equal to the max of the ceiling of C and n0, then I'm going to add 1 to that. So remember, this takes the larger of these two values. I'm rounding up C, so it's an integer, but it's an integer that's large enough. And the way I picked these two out was, remember, I looked at my inequality, right? It said n is, I suppose that n was less than or equal to C, right? So all I'm going to do is make the one side of the inequality larger and overtake the right-hand side, right? So, for example, if n is equal to the max of this, this value is larger than or equal to n0, but is larger than C, violating n is less than or equal to C for all n greater or equal to n0. And we have derived a contradiction. So the contradiction here, of course, is that under my assumptions, I was able to derive that n is less than or equal to C for all n is greater or equal to n0. And then I showed you, hey, look, I can show you that there will be some point where both n is less than or equal to C for all n is greater or equal to n0, and there's going to be some point at the same time that there will be values for n within that range that actually violate that inequality at the same time. Both statements can't be true at the same time. So yes. So somebody's asking the way they proved it was correct, like it made sense, but you could use similar logic when n cubed and always be less than n squared, since it is lower power. Yes, you can make the same argument at that stage. I just wanted to keep it simple so that it made it really easy for me to talk about this n value that I picked. It makes it a little easier for me to argue for it, but the point is that yes, if you want to work with a higher order powers, like my example here, you're welcome to do that. It's just that I just wanted to shave it down so it's a little simpler to play around with. But no, that's wonderful, wonderful. So are there any questions about what I did here? So remember, in a contradiction proof, you assume the negation of what you think is true, and then you take its assumptions to its furthest extent, and what you do is you show that those assumptions that you made cannot be true simultaneously with whatever follows from it. So you end up with a statement that is the case where your assumption, if it were true, you end up with a bunch of nonsense. So in this case, the nonsense was that I end up with a statement that most certainly can never be true. But to the point where, like, yeah, no, I can actually tell you exactly where it falls apart, right? And since the statement's domain is over n is greater or equal to n0, then yeah. We're basically popped the bubble. But yeah, no, so those are a couple different ways you could establish f is not big O of g. Are there any questions about that before we proceed to talk a little bit about big O properties? I put it outside this time. It wouldn't have mattered if I put the +1 right beside this c here. If I move this +1 to say the max of the ceiling of c +1 right here, it wouldn't have made any difference. I just felt like showing it that you can write like a +1 outside the max function. But yeah, this is outside the parentheses right here. Because I want to just make sure that, so for example, suppose that c is an integer. Just suppose that that is the case. If it is, then you know that you didn't violate the inequality. In fact, it will be equal to the right-hand side of the inequality. So this is why I include the +1. I need to make it a little bigger. I just need to nudge it just a little bit more. I just got to push it just a little over so it violates the inequality. So if you want to see what I mean, try putting in the ceiling of c here, right here, and imagine that the ceiling of c is actually an integer. If it's an integer, you have no rounding to do, so you'll end up with c is less than or equal to c. Well, n is a very specific number I pick out. So keep in mind that I could have picked n to be a bigger number, like it could have been the ceiling of c, or n0 as the max here, +5, for example. That's perfectly fine. Most certainly. There can exist many different values for n, but remember, you have to pick n big enough. Remember, n depends on c and n0 now, because I don't know what they are. But yeah, that's a wonderful question. Okay, so are we okay to proceed to talk about some properties of big O? Okay, so let me proceed. Let's talk about some properties of big O. So I'm just gonna give us some properties. I'm gonna list out some of these, and then we're gonna prove one of them because I want to make sure you see kind of the game plan for proving big O identities. Some properties of big O. So let's list out some. So the first one that I want to talk about, actually, let me first be clear here. We're going to have 3 arbitrary complexity functions. Let f, g, h be complexity functions. So I'm going to assume that they're any complexity functions. I don't know what they exactly are other than that they're a complexity function. So I have f, g, and h. I'm going to use these when I define the properties. So the first property that I want you to be aware of is the so-called transitive property. You might have heard of this if you're working on your homework. If f is big O of g and g and big O of h, then f is big O of h. So notice I'm just using this notation because it just saves me a little bit of time. So remember, that's all it's saying is. So if f is big O of g and g is big O of h, then f is big O of h. So this is what we would call the transitive property, or its transitivity. It's a valuable property for the sense that if you have some complexity function you're analyzing, and suppose you're doing some count of that, and you know that it's at least big O of g, but you know that your other function, say there's another one that's related to your analysis, but you know much more about that one. But you know that it's big O of h, you can conclude immediately through this property that whatever you're originally studying would be also big O of h. So just as an example of this being applied, so just as an example, I could tell you that n is big O of n squared, right? And n squared is big O of n cubed. So n is big O of n cubed. This is directly from the transitive property. So you could cut out the, I don't know, I don't like using this phrase, but you cut out the middleman in this whole thing. So you can go right from n all the way to talking about, f to go all the way to h. So that's one very useful property. Second property. So this is actually the one that's closely related to why we can often drop constants. When we talk about our big O notation, we talked all about how you could just drop constant terms. This is going to be that property. So oh no, I lost the turtle, Fred. I'll save you after, okay? If c is a positive real constant, and f is big O of g, then c times f is big O of g. So you can have a multiplicative constant that's also involved with your complexity function, and it'll get fully preserved as long as you know f is big O of g. So if you have an additional constant that's sitting, say you originally do some count of some operations and you introduce, say, constant number of operations on top of those. If you establish that f is big O of g, and if you just add in some constant number of operations on top of those by multiplicative amount, it doesn't matter. That's all this is saying. You can also take this and generalize it. So if you talk about, say f is 1 and g is 1, this is actually how you could say that some constant is big O of 1, for example. So if you ever find yourself counting those instructions or counting the operations, and you ever wonder where all those constants go, yeah, this property is the one that tells you, oh yeah, all those constant number of operations, they may as well not even be there. Okay, here's the next one. If f is big O of h, and g is big O of h, then the sum of f and g is big O of h. Now you might ask, Dan, why should I care about this property? So first let me reiterate it. So it says if f is big O of h and g is big O of h, then f plus g is big O of h. So you might ask, Dan, why should we care about this property? So think about it in terms of, say if you have multiple parts to an algorithm. So you have a first phase, then you have a second phase. So what I'm saying is if you analyze the first part of your algorithm and you determine that it runs in big O of h, and you look at the second part of your algorithm and you find out it runs in big O of h, then if you take all the operations between the first part of your algorithm and the second part of your algorithm, then the overall number of operations has to be big O of h too. So this is actually a nice little thing to keep in mind when you're doing analysis and you find yourself dealing with a really big complicated thing. If you find that you have an idea of what the big O should be, then you can always analyze the bits and pieces, then put it all together for the total number of operations. So that's one way you could use this. There's several other ways you can use this property. It's a very general one. It's not tethered to any one application. It's just a property of complexity functions with big O. Sorry, I'm getting really excited here. So I want to give you another property. So let's talk about one more property, and then I'm going to prove another property for you. And depending on where we get from there, that'll probably be where we're going to stop today. I was hoping we could start talking about recursion, but I think we're probably going to have to talk about that next time. So let's take a look. So let's I got one more property for you before we proceed. Now this one will take you back to playing around with calculus and limits. It's a very helpful one if you find yourself just really wanting to do some side calculation. And you're saying, hey, look, how can I know if it's big O of this other thing? And if you have offhand, you remember all your fun things you could do with limits, this is a helpful property. I will not test you on this property, just to be very clear. So I like to be very transparent about these things. So I'm going to be a little bit sloppy with this, but if the limit as n approaches infinity of f over g is not equal to infinity, then f is big O of g. So sometimes people refer to this as the limit theorem for big O. So if you know how to evaluate the limit for your f and g when it's taken a quotient like this, if you could show that the limit is not going to evaluate to infinity, then you could say that f is big O of g. So you'll find that this is a really helpful way if you need to quickly calculate out a big O and determine if it works or not. This is a helpful property for doing that if you remember back to your limits. One thing I do want to acknowledge is that this third property here, this one right here, we're going to try proving that here, and that's going to be the last thing we're going to do. So I'm going to try to squeeze this in the next couple of minutes. So please, I apologize if I take a little longer, because I want to make sure that you get to see this. So let's try proving property 3. Let's try proving property 3. So one thing I didn't mention is that often the third rule here is called the sum rule. So remember property 3, that's the one that says if f is big O of h and g is big O of h, then the sum of f and g is big O of h. So we're going to prove that right now. So let's try proving this claim. So remember, the third property is actually what we would call a conditional statement. It has if, this, and that, then it follows this other thing. So we're going to use the part that is the if part of the conditional statement, just like if you think of it like an if statement, for example. It has conditions. In the conditions, it says if f is big O of h and g is big O of h, I can take those and use those facts. This will be very helpful when you're doing your proof for the final part of the assignment. So here's the idea. I'm just going to lay out just like I did at the beginning of this lecture. We'll say we prove the claim using the definition of big O. Now, first, remember, I have as information, remember, this is the conditional statement I had over here. If f is big O of h and g is big O of h, those are two pieces of information I can use. And if I know f is big O of h, then that means I can use the definition of big O there. I know that g is big O of h, so I can use the big O definition there. What I'm going to do is I'm going to take these two things and bring them together to try to invent a c in n0 for my big O definition proof. So that's where they're going to come from. So So I'm just going to first point out what I'm going to invoke about these. Keep in mind, you can always say we need to find constant c in n0 such that da 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 da. You could also say that at the beginning. I'm just going to set up all the hard work up front. It's not too much of a difference here. Since f is big O of h, there are constants. There are constants. C1, I'm going to call them C1 and N1, just because it's a little bit easier for me to talk about C and N0 afterwards. C1 and N1, which is a positive integer, such that f of n is less than or equal to c1 times h of n, right? That's what the definition would tell me. And this has to be true for all n greater or equal to n1, right? So that's the first thing. I can invoke the other part of the conditional statement. So now I could say also G is big O of h. So there are constants. C, and I'll call it C2, just to keep it simple. C2, which is going to be a positive integer. Sorry, not positive integer, positive real number. Gotta make sure you get these two constants right. C2 is a positive real number, and N2 is a positive integer. Positive integer such that G of n is less than or equal to C2 times H of n. And this is for all n greater or equal to n2, right? Now this is going to be one of the only times you're going to see me pick n0 first. So watch this, watch this. It's going to be a little bit subtle. Now, let n0 be the max of n1 and n2. So I'm just going to make n0 be the larger of these two constants, so that this inequality should hold and this inequality should hold, both of them. So if I pick a larger value of n, this is okay, because remember, n0, if I pick any value that's beyond the smallest value that could have worked, or any value it could have worked, then I most certainly, it has to be true, right? If I pick a larger value beyond that original one. So let n0 be n1, n2. Now let me finish up the proof over here. I'm going to be trying to quickly wrap this up. I apologize for going a little longer here. But I want to make sure that you see the strategy here. So let's quickly wrap up this proof. We're actually just right near the end of it. So let's just finish this up. So remember, I picked n0 so that it's going to be large enough so both those inequalities are going to work. Then what happens is I'm going to sum over both of those inequalities, right? You know that I have f of n is less or equal to c1 times h of n, right? And we have that g of n is less or equal to c2 times h of n. I'm going to use the exact same strategy we used for our examples earlier, right? I'm going to take them into buckets and I'm going to collect them up, all of those terms. And I'm going to check against the left-hand side versus the right-hand side. The same strategy I used earlier. So then, f of n plus g of n is less than or equal to c1 times h of n plus c2 times h of n. Which this is, if I were to notice that both of these are h of n terms, I'm going to take h of n together. So I'm going to have c1 plus c2 times h of n, which this holds because of my selection of n0, which holds for all n greater or equal to n0, because I picked n0 to be big enough. Now, any questions? Actually, I have a question quickly for you. What should I pick for c? I'll give you a hint. Pretend this part I have in the middle is not there. Just read this f plus g part and what I have over here. Remember back to the definition of big O. Yes, you take the sum, you make C is going to be C1 and C2 added together. Perfect. Perfect. So, choose C is equal to C1 plus C2. Then f of n plus g of n is less than or equal to C times h of n for all n greater or equal to n0 as desired. Therefore, the sum rule is true. And that's the end of the proof. So notice that when I prove these types of identities, I don't know what f and g are. They can be any complexity functions. The idea is that you use the definition of big O. You spell out what that means, and then see if you could take those parts that you have from the definition invocations. So the definition of big O, it tells me I have those pairs of constants. Then I had my other definition of big O I invoked, and another pair of constants. What I do is I take those together to try to come up with a statement that looks just like the big O definition that I wanted to establish for the identity. Okay? So first, I apologize for going a bit longer. I'll make up for it next time, okay, everybody? So I want to say thank you very much, and have yourself a beautiful evening. I'll see you later.